Good afternoon, everybody. Thanks for coming to my talk instead of having an undoubtedly well-deserved nap. We're going to talk a bit about floating points and elevating precision of floating points today. So I have a bit of a menu there, discuss what floating points are, how they work. All the people who went to Casio's excellent talk this morning I will have to disappoint you, but repetition is a important source of learning. So here we are. I'll talk about modern C++ and floating point times for a bit. We'll discuss something old called Dekker doubles, but that's still a hot topic. And then we'll have some kind of a demo. Now, don't worry. I am a teacher, so I know about live demos and what you call upon yourself with the elder gods if you try to do those. So I have screenshots which I will be using instead of trying to switch screens while I'm recording something. I have learned those hard lessons. I teach, by the way, at Digital Arts and Entertainment. That's a school in Belgium. We were the best school for game development 3 times out of the last 6 or 7 or something. It's not us who say this, but an independent ranking as a public institution. We are very proud of this. So what are floating point numbers? I think I don't have to explain what they are. Everybody knows what they are. What's a bit surprising, though, is as programmers start in their careers, the first things they hear about is strings and integers, booleans and floats. And everybody knows how strings work. Everybody knows how integers work. Everybody knows what a boolean is. And almost nobody seems to know how floating points work. They just work magically. They seem to be there and work. So this talk is as much an attempt to demystify what's happening behind the screens as it is a demonstration of some other new ideas. We're not mathematicians. Mathematicians have real numbers and they are all the numbers. That's why on the top you see this gray bar there. I am telling you nothing new. Again, if you went to the talk this morning, you have 0 in the middle. Or floating point numbers manage to represent some of these real numbers. As we move away from 0 and the numbers get larger, I mean, an absolute value that is, the error we make has to become larger as well. Fortunately, the relative error remains low. Now, before I show it, because it's an animated GIF and it will start automatically, I will tell you something about what you will see on the next slide. I have a picture of a car. A car, for those of you who are not used to computer graphics, it's made out of triangles, right? Very tiny triangles. Real cars are not made out of triangles unless it's a Cybertruck or something. But I will be moving this car away from the origin, but using absolute coordinates. So this problem that we have with these margins of error getting larger, we should see something happen. Let's see what it gives us. So here's our car, it's moving. It still looks fine. Oh, stuff is starting to happen. Errors get introduced. And you can see as you move further and further away from the origin, your car definitely starts to look less car-ish. Well, since I talk about game design as a living, how do we solve this in games? It's actually pretty simple. We do not draw stuff starting from the origin. Right? Everything is drawn based on relative coordinates to solve this problem. So we draw the car based on the object is placed there, and then we'll use relative coordinates for that new origin. I did not make this animation. The source is in the bottom. On my slides, I have quite a bit of online resources. They are all mentioned both in the comments and on the slides. I hear they will be made available, so you can look at them at your leisure. I will wait a little bit until the image comes back. Okay. So here is the part where I would do a demo where I'm not recording this, but that's not a problem because I know how demos work. There's a guy who has a site, H. Schmidt, and I like him. I don't know him personally, but he has a very nice online floating point converter. I encourage you to go and see it, and it's very nice, right? You can just set some bits and see what it does, or you can enter a number and then see what you store. When I show this to my students, or even sometimes to quite experienced programmers, nobody is surprised that you cannot store 4.2. What you store is 4.1999, etc. There's a certain error you make, and then there's a hexadecimal representation. All not surprising news there. Where it gets more surprising is when I store an integer number. I've stored 1, 2, 3, 4, 5, 6, 7, 8 there. Well, it works perfectly, right? So you can store integers without problems. Yes, yes, and no. Look at this integer. I can store it in a floating point, but I'm 3 off. Remember, though, as those errors grow larger, it's not magic, right? We have a limited number of bits. As we store more and more things, something has to give at some point. Now, a very practical issue is if you're using floating points for something, by the way, if you're using it for money, don't. Never use floating points for money. If anything, if I can teach you anything today, don't use floating point for money. Right? I think I need to explain this to no one, but still, as a teacher, I'm used to saying things that I thought were obvious. But if you want to know how many digits does it represent, of course, C++ has us covered. In the numerics library and numeric limits library, you can ask, hey, how many digits can I represent using this or this type? Again, I have all the code I show. I have Godbolt links. Actually, I think Matt Godbolt prefers to call it Compiler Explorer, but I'm so used to calling it that, it's going to be hard to change. Also, it's shorter to type, which my laziness and habit, that's going to be a hard thing to break. So I wrote a little bit of code here, right? And I just see out the digit for a float. I look at how many digits can a float do. A float can do typically 6, a double 15, and a long double 18. The astute among you will think, well, that is weird. Only 3 digits more for twice the storage. Well, yes. We'll get back to that in a bit. If you use a 128 bits long, you will usually only get 80 bits. And why is that? Well, because fuck you. No, the real reason, of course, is historical reasons, right? It has to do with Intel x87 coprocessor, and they needed added precision, and they had this internal 80-bit representation. And you can use this with a long double if you want. Don't use long doubles. I'll show you the alternative in a bit. Okay, part 1. We just double check to see how we're doing on time. If I talk too fast or too slow, it's hard for me to know these things. Now we're gonna get to how floating points work. Cassio, I'm sorry. I'm gonna say the same stuff you said. Fortunately, we're saying the same thing. It would have been quite embarrassing if I had a completely different story. So it's really based on a scientific notation, right? So you have some part that's called a mantissa, some exponent, and something to represent signs. I hope you all remember scientific notation. For some of you, it might be quite a time ago. But how did scientific notation work? It's a universal way, an easy way to write numbers the same way. It's one digit followed by a dot, and then the rest of your digits times 10 to some power. Of course, when we do binary stuff, this will be powers of 2. An important thing to remember here is that this first digit cannot be 0, right? It's the first non-zero digit that you put there to have a uniform way of representing this. This gets important later when we talk about how they really implement it. How to re-implement it is in binary. Think about it. If your first digit is non-zero and it's binary, then it's always 1. So why would you store it? Of course, there's a denormalized floating point numbers. I will not go as far as to discuss those. Right. This is also interesting. The word mantissa, people seem to like it, but sometimes they talk about coefficients, sometimes about argument, sometimes about fraction, or even characteristic. I did not make all these words up. This is a copy from Wikipedia. So if confusing you see one of those other words, they also mean mantissa. Again, because this is all too easy and making different words mean the same thing that are slightly confusing just helps. So how does this all look in reality? I have, due to the same constraints as the talk this morning, decided to go with just floats, not doubles, because then I can show all the bits on one slide. Could have gone with 16, but that's very new. You have one sign bit, that's 1 is easy. If it's 0, it's plus. If it's 1, it's minus. So that's great. Then you have a couple of bits that represent your exponent, and then further down the line you have more bits that represent your mantissa. And if you add them all up, you get to 33 because one of the mantissa bits is implied. Remember that one I was talking about? It's always 1 point something something. The first digit has to be non-zero, it's binary, so this one is implied. This representation we're discussing, by the way, is called IEEE 754. It also has another stupid name. I'll get back to that as well. Some people mistakenly think that this is mandated by the C++ standard. As many things, it is actually not. It's usual, but you can perfectly have hardware that supports some other exotic form of floating points and represents it differently. So it's not recommended that you count on how it is represented, how the binary form is represented to do stuff with it, right? If you want to do bit trickery and bit magic, that will usually work. That's the kind of problems we love, right? And then your software gets released on some exotic old platform and then it doesn't work. Or it's mysteriously. It works on my machine, everybody's favorite excuse. Long double, for instance. I'll still move off the platform maybe a bit. I'm sorry. Long double, for instance, right, is not typically implemented by something mandated by IEEE 754. There's a 128-bit format, but there's also an 80-bit format, annoyingly. On PowerPC, there's something called a double-double. More about those later. So well, we can do a little bit of mathematics, right? -1 to the power sign bit. Sometimes I have to remind my students something to the power 0 is 1. So that's a clever trick, so you don't have to write an if. 1 plus the decimal mantissa times 2 to the exponent. That's how this stuff works, right? The 8-bit exponent is not signed in the way that we're used to an integer with 2's complement, but it's just biased. That gives us some advantages, which we will not discuss here. It also helps in sorting. It makes it slightly easier for some of the hardware to be implemented. So just remember that you have to subtract stuff from your exponent if you ever do floating point calculations by hand. I hope that you never have to, unless you're writing a very cool new dragon that's even faster than the 7-headed one we saw this morning. You never know. It will not be me. So this is the single precision, right? The normal float, 8 exponents bits, 23 fraction bits, assigned bits, and then the implied bits, right? There's also double precision. Look, I managed to fit it on the screen. You just have to believe me that those are 52 bits. Actually, they're not. I will give a bonus to anybody who knows from me. No. Actually, I stole that image from Wikipedia, so it's probably right. There's 11 exponent bits and a sign bit as well. The bias here is 1023. It's the last 10 bits. Something relatively new, well, new and not new. Half precision. Who has heard about half precision floating points? Yeah, some people have. They're used extensively in gaming. GPUs have been supporting them for a long time. So is C++ nowadays, fortunately. Well, nowadays in a very late standard, and they have given them a sensible name. I was really scared that they were going to call them short floats or something, but no. But we'll talk about those names in a bit. Again, we have only 5 bits here, so lowest 4 bits, 16 minus 1. That's that 15 that you have to use for that bias. Those half precision only have been added to IEEE 754 since 2008. So that's pretty new stuff. Why are they used for things that are not super critical precision-wise? You can put many in a long register and then do multiple calculations at the same time. I heard earlier from someone that then NVIDIA will claim you have twice the speed, which is, of course, nonsense. It doesn't work like that. But, I mean, as a general idea, you can do twice as many calculations. Okay. Let me double check where we are on time. Yes, very good. Modern C++ and floating points types. You could be wondering, Tom, why are you talking about floating points? This is old. Everybody knows those. They've been around for forever, but it's still a hot topic. Things are still changing. C++ 17 saw the introduction of the floating points literal and hexadecimal format. So even if you can't use very modern C++, C++ 17, you can already use hexadecimal representation, which is nice. Keep in mind, however, that you're not guaranteed that it's IEEE 758. It should be on most of your machines, unless you're working on really exotic stuff. If you do, I'm really interested. Come talk to me. More interesting, what has happened in C++ 23 for your literals. You all knew you could add F or L, but now you can add F16, and it's not a plane. It's a 16-bit float. F32, F64, F128, and BF16. Does anybody know what a B float is? I'm always pleased if I can show something on slide that nobody knows. So at least I have taught you one thing. I will come back to B floats in a bit. As I said before, I have plenty of trust issues, so I'm not doing live demos. All the code I am showing, of course, again, is on the link that you can see there. I'm cheating against several rules here. Look, I've been really old school. I wrote a macro. It's nice and compact and serves my purpose right here. What does this bit of code output? Right, it outputs depending on how you define stuff. Right, with all the new ways to define literals. Look at how cool it is with those hexadecimal numbers. You can use the ticks in between if you want to make something more readable. For instance, there are people who memorize pi. They usually memorize them by 2 digits. You can put ticks in between if that helps you read it better, right? 3, 14, 15, 92, etc. And then you can just print them out. By setting the print width to 16, I can force it to give me as many digits as possible, right? So this is how you can use all these new literals. I think there's nothing shocking here for anyone. Now, these are the new floating points. types that have been introduced in C++23. The half precision that we talked about, float 16. Thank you for a good name also, the standard committee. I love you for not having gone with short float, because what the hell. Float 32, which is just a standard float, but it's nice to have a logical name. Float 64, float 128, and then the B float. I will already tell you what the B stands for. Anybody wants to take a guess what the B? What? No. Other guesses? What? Brain. They're actually called brain floating points. They're a floating format that's especially convenient. By the way, before I gave this talk, I had to look this up as well. They're used in neural networks. Apparently, when doing neural networks, it's more important to have a wide range than to have high precision. So if you look at the normal 16-bit float, it has 5 bits of exponents. The B float will have 8 bits of exponents, allowing it to have a wider range, right? But of course, with fewer precision. This is there's no free lunch in this, so both are supported. Okay. Exciting. Now we arrive at Dekker doubles. Does anybody know who this guy is? Anybody? No? I will give you a hint. It's not Moss from the IT crowd. What? That's one person less you have to think about. I will get back to our mystery guest in a bit, but I want to do a little bit of a thought experiment with you guys. And again, I'm sorry because we already did some kind of thought experiment like this morning. But imagine we have some kind of a 2-digit floating point system. I won't even think about, and we're thinking decimal right now, right? And I won't even think where I'm storing the exponent. So I have a 2 digits, I can store 48 or 4.8 or 48,000 or 0.00048, right? I can store, that's my system. I can store numbers with 2 decimals. 2 digits, I'm sorry. Now I wish to add these 2 numbers, 51 and 6.3. They both fit in my system. If I add them up, I end up with 57.3. Does anybody see the problem here? I can't store that. Well, shit. Well, I can store 57. So that's nice, right? So my result R is 57. Now, what if I want to calculate the error I've made? I will call this small r, right? I have big R, which is my result, and my error is a small r, which is the x minus the r plus the y. Now, if any of you here are mathematicians, you will tell me, Tom, that's nonsense. Because r is x plus y, and then I do some magic, and then x minus x plus y minus y, that's 0, right? But this is not mathematics. This is, no, that's not the right slide. Sorry. This is C++ for the people who came to John's talk, right? So we'll take advantage of the limitations of our computer, and we'll do the things step by step. 51 minus 57, that's minus 6. Minus 6 plus my y, that y was 6.3. So my mistake is 0.3. So, again, we're doing a thought experiment here, right? So actually, I can store my entire number by using 2 of my floating point number. Big R, which is the upper half of the result, 57, and little r, which is the mistake I've made, but then it's a second floating point. So together I have 57.3. This is called double arithmetic. Again, this was just a thought experiment. We'll go in a bit more detail about how this works. It's just to give you an idea what we're trying to do here. So we can't fit the precision we want in a single floating point. We'll use two. To do this correctly, this will require some effort. Let's get back to our mystery person. Remember our mystery person? We know who it's not, but who is it? It's Theodorus Dekker, also known as Tony by his friends, I've heard. He's actually a Dutch computer scientist and a pretty famous one. He was one of the first. Well, he is attributed the first mutex algorithms. So if you work with mutexes now, thank this guy. So his arithmetic is called Dekker double, not to be confused with. Wow, somebody laughed at my stupid joke. I'm glad, thank you. So yeah, he's actually famous for Dekker's algorithm, which is not related to this double arithmetic or Dekker double arithmetic, but for basically the first proven mutex algorithms. About his arithmetic, he has written a very interesting paper in the 70s. You can still download it. It's a very civilized paper from another and better age. And I'll just talk you through how we can do some calculations using his system. We'll do a second thought experiment, and here I'm gonna need some kind of notation, right? My Dekker double is gonna be an uppercase and bold letter like A. An uppercase A is gonna be the upper value, and a lowercase a is gonna be the lower value. So here I have two numbers, right? 37.51. The upper half is 37, the under half is 0.51. 126.8, the upper half is 120, the bottom half is 6.8. Now, what I wish to do is I want to calculate C, which is the sum of those two. Without losing any precision, of course. I mean, I only have doubles with 2 digits of precision. I want to have 4 digits. I'm using 2 of them. How can I do this? Well, Dekker's addition algorithm has 5 steps. We add the upper halves. So far, I think we can manage that should work. Then we find the error. We just discussed this, so that should also work. We add the lower halves and the error. We allow this to overflow into the upper half if need be. And then we remove any overflow from the lower results, and we're there. It's actually, if you think about it, not very complicated. But let's go through these steps just to give us an idea. I try to keep the numbers there in a little black window so we don't lose track of what we're doing. So I'm calculating my result, the upper half, that's just A plus B. That's that 37 plus 120. That's 157. But I cannot store 157 in R. So I'm storing 160, which is the closest one I can find. Okay, next step. My intermediate value, I keep it there in the top, 160. Now I have to find the error. We had our little formula for the error earlier, right? Remember, I had my x minus my r plus my y. So I have my b minus my r plus my a. 120 minus 160 plus 37. The mistake I have made is minus 3. So my mistake I have made is minus 3. Does that make sense? Yes, yes. I wanted to have 157. I stored 160. So I have my solution. There's a little bit of a trick here for precision. Depending on which of the two numbers has the highest absolute number, you need to use a different formula. When we get to how you code this, and this if will also be there, right? So the error we made in R gets added to R. Yes, we have done this. It's minus 3, right? So R contains the error plus the sum of A and B. So it's R plus A plus B. That's minus 3 plus 0.51 plus 68. That's minus 2.5 plus 6.8. That's 4.3. 4.3. Remove any overflow from the lower result. Right? No, I'm fine. I'm okay. So my result is 164.3. So the total results is 164.3. The results I would have had theoretically of my 37.51 plus 126.8 should have been 164.31. Of course, I cannot store this. I cannot. So 164.3 is pretty close. It's as close as we can get. So yeah. So now we understand the principle. We know C++. This is C++ conference. Let's look at what we can do in practice with this. I will very briefly show you some code, but don't hold that code against me. The first time I heard about these double deckers, it was from a YouTube video. The link to that YouTube video is also at the back of the slides. And I took a screenshot from the code it provided. It's terrible because that's totally not how you would do it, right? I mean, yes, it adds and it uses two doubles, but it's clear you would like to have some kind of class for something. So let's look at the original source material and see if we can do something smarter. Let's do a blast from the past. Here I have some screenshot from the original paper about addition. This is in Algol 60. I don't think many Algol 60 slides have been shown at cpponsea yet. It's surprisingly readable, right? We have some procedure to add 2, which takes x and xx, y and yy, and then the output will be z and zz. They're floating point numbers. So they use the same assignment operator as in Turbo Pascal, right? The colon followed by an equals. There's an if here, and you really define a procedure here. Let's see what we would do in C++. In C++, I'm defining an operator. I'm not very happy that I chose DD for the name of my Dekker doubles, but the nice thing is you can choose whether you think it means double double or Dekker double or even double Dekker, to which I pass the left hand side and right hand side, and I'm doing this calculation as described in the paper. As you can see, this is pretty simple, and actually most of the calculations are pretty simple. What seems to be very hard is to print out these numbers. So I have a new friend who will help me find a way to do this. I see he's very excited already about this. So this addition, there's also subtraction. If you look at it, it's more or less the same rules. There's also an if to do with precision. Again, we've created an operator for our DD class, so it's a friend of the DD class, and we try to write that in a more or less clear style. Again, all this code is available on Godbolt. I don't know. Well, it's in anyway. The link is in the comments, but there's links in the slides themselves a bit further as well. So addition and subtraction seem to be pretty simple, right? We've went to an example. It's pretty intuitive to understand. It gets a bit more complicated once we want to start multiplying stuff. Once we want to start multiplying stuff, well, we'll need some helper function. And this helper function, the first one is pretty straightforward. I want to take two normal floating point numbers and multiply it into, that's why it's called multiply 1, 2. It's it's two normal floating points into a Dekker double, right? So I want to multiply those. So this is my multiplication code, and it's actually pretty simple, and it's a bit suspect as well because it's way shorter than this. What have I done? Well, you might notice in later revisions of other people who have used the technique, they have split out a function that is called split, right? So with split, you can take a double number and split its precision over two floating point numbers and create a double number. That's a feature that you need. What Dekker originally did, this was built inside this function. But since you need it for some other stuff, if you want to do a square root, you also need it. So it's handy to split it out. So I've inspired by some people, I've written my own split function, and just because that's the kind of guy I am, I immediately cheated against the rule I told you earlier. Don't count on it to be IEEE 754. But I have reasons. Terrible reasons, but I have reasons. So I have this function called split. Again, I'm doing terrible things, but at least I'm doing assertions. I like assertions better than comments, right? Because people don't read comments, but your compiler will read your assertions. I want to make sure the size of my input is 8, so that doubles mean what I think they mean. I'm gonna need a long at some point, so I also want it to be 8 bytes large. And then I want stood numeric limits of the type of inputs to be IEC 559. Thank you, all the people who make weird faces at me. I made the same weird face. This is the C++ we know and love, right? In C++, if you want to know if something is IEEE 758, you need to check if it's IEC 559. Because apparently that's a different name for the same standard, and that nobody knows. So of course, that's the one we picked to put in numeric limits. So if you ever hear about IEC 559, it is actually IEEE 754. The advantage is IEC 559 is the IEEE 754 standard of 2008. So it's the latest version. I don't know what will happen if there's a new version of the IEEE standard, but here we are. So what do? I make sure it's going to be represented the way I explained to you guys, right? And then I make a mask. This mask is really simple. If you think about it, I just take the bottom 27, 26. I can count really, 24 plus 2. 26. I take the bottom 26 bits. I set them all to 1. That's that constant. And then I put that little thing. That's not a destructor here, but inverting all the bits. So I invert everything. So that makes that I mask off the last 26 bits of the precision. And I mask this. And now comes the reason I wanted to use this terrible method to do it. Finally, I could show my students bitcast. Look, bitcast. How fast does this go? Normally you need several lines to do this. You can just bitcast that into a temp. So I turn it into a long. So because I need that to be able to do the masking, and then I just bitcast it back into a double. Terrible, terrible, terrible code. Never do this. But it's very fast, right? It's very fast. And if you know for sure, which I make sure of with my static asserts that you're using IEEE 754, this is perfectly valid code, but you shouldn't really be counting on how something is represented to split. Since I have split up, I have removed all the bottom bits. Remember the beginning of the talk and the very good talk from this morning. I have removed all the bottom bits of the mantissa. So I only have the most relevant part left. If I take the original number and I subtract this, then I get the remaining part, which is the lowest significance bit. Perfect. So this is how I can split this. But of course, I know what you're thinking. I see the look of disappointment. Tom, you're using these dirty bit tricks. Dirty bit tricks. Yes, I'm sorry. There's also another way to do it. Actually, if you're not IEEE 754, this is guaranteed to work. If you think about it a bit, you will understand why. I will not discuss it in detail. The guy who came up with this version is called Veldkamp. It's pretty new stuff, all of this, surprisingly. And what I'm furthermore was very surprised about, because I was thinking, I'm going to go give a talk about floating points. This is not a hot topic anymore. Well, isn't it? I don't know. Look at this. Veldkamp Dekker algorithms with directed roundings. But might I point your attention, well, it's maybe hard to read from where you're sitting. Preprints submitted on the 27th of February 2024. Active work is still being done on this stuff. So I'm not crazy. My mother had me tested several times because she didn't agree with the results. Now I have my split. I have my multiply 1, 2. I mean 2 doubles, and so now I can do my multiplication. Look at this. That code is pretty simple. Once you have your multiply 1, 2, and then multiply 1, 2, we use that split again. We've written some code right here, right? The multiplier. Look at it. It looks beautiful. I use that multiply 1, 2. I make a new double right there called middle, and then I use my intermediate. And now I can add, I can subtract, I can multiply. In the Godbolt code that I provide, I have also done division to be sure that it works correctly. But yeah, we've done all this work now. We've looked at algol, read a paper from the 70s. You've had to listen to me. I know this has been a very tough afternoon. Where are we now? Well, it's demo time. And again, I have taken screenshots because demos, we all know how well those go. The compiler explorer demo code, the links are in the slides. If you want to look at it or copy some codes, feel free. Is there anybody here who does not know Quickbench? Everybody knows Quickbench is great. You can do great tests with Quickbench. It's like Godbolt, but instead of just running your code, it runs performance on it multiple times, so you can get statistically relevant numbers and you can compare functions. Great stuff for tiny examples like this. So this is the test that I've made. I'm going to be honest here. This is not a super scientific test of the precision. I could have done more in that regard, but the advantage of doing simple tests is they're a bit intuitive and they're easy to understand. I just define some number. Here it's 1,000. I say the number of loops I will go through is the square of that. And then I define something called difference, which is 1 over that number. So if you think about it, if I have 1,000 and I add it up to itself 1 million times, I should get 1,000 again. By measuring the difference, I have some idea of precision. Is that super scientific? No. Do I care? Well, it's a demonstration. It's to get you introduced to the concept of using double deckers, also to convince my new friends so he has to adapt his dragon, make it 8-headed dragon that also does double. Maybe 14-headed. Anyway, and I see out the results to show what it gives. This is what I get from Godbolt. Get a pretty big error using just floats. I mean, it gives you an idea of just 1 million time adding 1,000. You should get to 1,000. You're already 9 off. With a double, well, you're 1.6 times 10 to the -8 off. With a long double, you're -8 times 10 to the -13th off. With a Dekker double, you're an order of magnitude less of a mistake you make. So that's good news. Yeah, but that's Clang. Visual Studio, of course, I've tried this as well. If you're wondering, why are long doubles the same, make the same errors as doubles? Because long doubles and MSVC mean nothing. Microsoft is lying to you. If you type long double, you just typed long for nothing. So just training you may have muscled fingers after it, but that's all it will do. That's also why I put the size off after it. So you see, we can actually increase precision. So that's interesting. Even with if you don't have the C++23 stuff yet, and you don't want to do assembly, you might use Dekker doubles to represent your stuff. There's no way to print them yet. Oh, I mean, you can print both of the doubles separately. That's not ideal. But I hear a solution is in the coming. I'm sorry. I struggled because I actually tried to print them out, and it's it's non-trivial to. You have an idea? Let's talk. Well, so far the good news. Now the quick bench. How well does this perform? As you see, yeah, it's not terribly good. Of course, if you think about it, even to do an addition, see all the calculations we had to do, I'm not surprised it's like a factor of 5 or 6 slower than it should be. Now this has already been, for me, an interesting exercise, right? But it's still been just an exercise. What I really still need to do, and I will do because it's interesting, not just the printing. But of course, I want to make a template out of this. And I want to be able to use that template recursively on itself. Should also work, right? Why shouldn't it work? That's why I needed another split method than the one I had. And I need to use concept to make sure it's floating point or another of those templates. So that's work in progress. I haven't done that yet, but I'm actually very much looking forward to it. Some references. So that's the YouTube I talked about. This guy discussed it. He's very good in introducing what it's about. The code itself he shows is terrible. That's that floating point converter that I cannot recommend enough. If you're not used to how floating points are represented, you can learn so much just by digging around with that tool. And that's it. I thank you all for your attention. And please, if there are any questions, I will probably not be able to answer them, but shoot.